finding the volume of pyramid today. So let me draw this thing. Here's axis, about that big. And let's turn that to black. And I want to have a pyramid here, so let's see if I can do this. Do I get to rotate this thing? This is annoying. Why is it selecting both of them? Let's see. I don't get to rotate this thing, so forget that idea. I'll use this technique. So suppose I have this. Now, this is a sideways pyramid. If we have this thingy, half of it sticking out of the page and the other half going in, do you see the pyramids with the square base sideways? Right? But we are not rotating it, so how are we going to do this, right? Well, I have an animation for you, so let's open that animation. File, calculus in motion, volume by volume on base. Okay. Now, this is not exactly pyramid, but this is a spectacular picture. Suppose, I wish you can see me. There is a rectangular slab and that is sticking out on a base. So some kind of futuristic opera house looking building. Okay, you see it. So now, watch this. What's going on? This is the picture. My God, right? Suppose we create this. Right? So if you look at it from the top, it'll look like circular shape. However, if you look at it from this side along the x-axis, it'll look like square. If you look at it from this side, it'll look some parabola looking dome thingy. Can you imagine this thing? Wow. Okay. In my classroom, there's a model of this thingy. Actually, I do have a little model that you can touch in the classroom, but hey, this is distance learning, so you can't have that. Okay, but there's other designs, okay? So let me create this solid. This one is using isosceles triangle. So it's even prettier. Bunch of triangles, cross section on a circular base. You know what I'm saying? Okay, the next one is my favorite design. Ready? Oh wait, what's going on? Right triangle. Some kind of opera house in Sydney. Beauty, eh? If we use a circular base, it tends to create the prettiest designs. There are a bunch of these projects, art projects, hanging on this, literally hanging from the ceiling of my classroom. That's usually after the AP, we have a project. I'm not sure if we will ever get there, because putting you into the group of 4 during this pandemic is really bad idea. So I'm not sure if I'm gonna do that this year, but hey, this is what I usually do. Now, does not have to, this is a triangular base now, okay? And using semicircular cross sections. Right? Okay, the next one. This is pyramid, so This one is not as good, right? So this is basically kind of what we are doing today, except we are using square as cross sections, okay? Alrighty, any question on what we are doing? Okay, now we'll go back to our note. So if we create a rectangular slab with a square looking thingy, I'm gonna draw it right there, right? So this is the X, and this, we'll call it this much S. Good. So that we have a pyramid, and this height from here to here, this is H. So that height inside of the pyramid is H. And then we have, oh, that's not S. This is S. I'll say S over 2 here. Good. So that we have a base S. Good. Now we have to create the volume of this little thingy. Okay, so our dV looks like this. This thing takes a lot of care. You know what I mean? This is my dV. Okay, so as before, this thickness is dx. Now, this whole thingy, do you see this much is y, right? Once again, x, y. So does that tell you this is 2y? And this is 2y. Do you see that? So my dV at the moment is 2i quantity squared times dxa. Okay, all we have to have is the function. So somebody tell me what this function is. Y is equal to? Oh, come on, we have done similar thing before. Ethan.
S over 2h and x.
S over 2h times x. You all see that slope is denominator h and numerator s over 2a. So we substitute that in here. So wow, this is convenient because that 2 cancels this 2. So we'll have s squared over h squared. And then we have x squared. Eh? Now we are ready to integrate. So the volume is from 0 to h. And then s squared over h squared x squared dx. Now that, of course, is s squared over h squared constant outside. And then I'm going to have x cubed, therefore 1/3. So what we will have is 1/3 s squared over h squared. And then, well, what did I put dx there? This is from 0 to h. So see, h cubed cancels 2 of this. So we have s squared h. S squared, of course, is the area of the base times h. And there's that 1/3. Remember from geometry, your geometry teacher taught you that there's a 1/3? Yeah, this is that 1/3. How about that? It takes calculus to prove this thing, huh? Okay, any questions? Well then, well, this is just a regular pyramid, right? What happens if we have something like this? Right? Some kind of slanted pyramid with, I just put pentagon, but whatever, right? So I'm gonna say this is the area, base area. Fancy base, I'm gonna put it in red. So this is fancy base area, right? What is the volume of this thing? This volume was still 1/3, and then base area times h now, wasn't it? How are we going to prove that? Well, this we have to get a little creative. So let's say from here, what? This computer is doing something weird today. That's my mouse that's not functioning properly. Say, suppose we have this thingy. Okay, this is my h height. Okay, and then I'm going to have the other distance from here. Oh, wrong direction, huh? I forget it. I'm going to restart. My mouse is not functioning today. From where the slat is. And suppose I'm going to call this thing x. Okay, so we got some dimensions, right? And of course, this thing has some kind of thickness. And that thickness I'm going to call dx. Y'all got the dimensions down? Okay, so I'm going to call this area of the pentagon, or whatever the shape that we are looking at, still A. Good? So my dV at the moment, I'm going to put dV here. My dV at the moment is A times dx, isn't it? It's a little slat with a thickness dx and an area A. So only thing I have to do is figure out what A is. How can we do that? Okay, I'm going to figure it out down here. And the question is, what's A to our surface, our area A to B? What is that proportional to? Would that be proportional to x to h or not, is the question. Think back in geometry. Is this true or not? Scale factor. That's a hint, scale factor. Okay, don't remember. I think this is like 7th grade math. It's proportional to the square of that. Let me prove it to you simply right here. Okay, it's not that hard to prove. Say there is a square, and let's say we dilate it to this size. Do you easily see that this is 1, 2, 3 square? You know what I'm saying? You see why we have to square it? Because we are extending it both x and y direction. Well, what happens if this is not really that, but suppose this is 3D shape while we are at it? Rubik's Cube. You see now it has to be 1 cube to 3 cube. In case you're dealing with 3D shape. if they are similar shape, then it has to be that ratio. So that's a little bit about scale factor. So coming back here, since this is 2 dimension to 1 dimension, we have to square the 1 dimension in order to have a dimension match. You know what I'm saying? You get this ratio? This is 7th grade math. Come on, people. Okay, then. Now come back here. So we have this A. Now we can substitute to x over h quantity squared. You get it? So, oh, a's from here. I guess I finished it. From here, your a is equal to, of course, your b times x squared over h squared. Right? Okay, so I have your b times x squared over h squared dx. Is my dv. Good. So my volume will be from x is this a vertical now distance running from 0 to all the way to h. And then we have b times x squared over h squared dx. Good. So yes. Okay, taking b over h squared out as a constant, and then I will have x cubed. So once again, we have this 1/3 from 0 to h. And substitute h, cancel 2 of them, so we still have 1/3 base area times h, as your geometry teacher taught you. Amazing, isn't it? Huh? Yeah, I know. I really amaze myself.